So the second derivative test for maxima and minima, the test states that if the first derivative equals 0 and the second derivative is negative, what we learned in that last activity is if that second derivative is less than 0, it means our function is concave down. And if the derivative is 0, it means we have a potential max or min there. So if we have a function that's concave down and we know there's a max or min there, then we know that that particular one is a maximum. Conversely, if the first derivative is 0, so we know we have a turning point, and the second derivative is positive, that means concave up, that gives us a minimum. So it would look something like that. And if the first derivative is 0, we have a turning point, and the second derivative is also 0, then that second derivative test is inconclusive. And so then they tell us just revert back to that first derivative test for the local extrema. So let's do the second derivative test on this particular function, which we've done before. So we can see the first step is we need to know the first derivative. So step 1, first derivative. First derivative of 4 is 0. Negative 3x squared, we get negative 6x. And x cubed, we get 3x squared. And we set it equal to 0. Here we have to factor. I'm going to take a 3x out of both terms, which leaves me with a negative 2 plus x. So I get x equals 0, and I get x equals 2 if I set each of those equal to 0. So these are my two turning points. That satisfies this if part up here. I can see the second step then is to show that the second derivative equals 0 and find where it's positive and where it's negative, that second derivative. We're going to do one of those test points. All right, so second derivative, I'm going to take the derivative of this piece again. So the derivative of negative 6x is negative 6, and the derivative of 3x squared is 6x, and we set that equal to 0. So I'm going to add 6 and then divide by 6, so I get x equals 1. And I'm going to use that second derivative to test these points. So now, second derivative, left of 1. I'm going to pick 0. If I plug in 0, I get a negative. And then a number to the right of 1, so I'll pick 2. If I plug in 2, I get a positive number. So because I used the second derivative, my conclusion here now is that this function was concave down on the left of 1, and it was concave up to the right of 1. So if I look at my two turning points here, x equals 0 falls in this range on the left-hand side. I'm going to just write x equals 0 over here, and x equals 2 is over here. So now we're going to write our statements. We're going to say at x equals 0, f prime of x was 0, and f double prime of x was less than 0. And so if I look up here, f prime was 0 and f double prime was less than 0, means it was concave down. So that gives me a maximum. So x equals 0 is a maximum. So notice you're stating all of those conditions, and then we're writing our conclusion. So a similar statement here would be at x equals 2, f prime of x was 0, and f double prime of x was greater than 0. So x equals 2 is a minimum. Now, we could have gathered that using the first derivative test as well. So just to review that, oops. I could have used the first derivative here. To the left of 0 would have been a negative number. If I plugged in a negative, I would get negative times a negative, which was a positive. A number between 0 and 2, like 1, I'd get a positive times a negative, which is a negative. And then if I plug in a number bigger than 2, like 5, positive times a positive. And so I can see it changes from positive to negative, and then from negative to positive. So max at 0, min at 2. And that's exactly the same thing that we gathered over here. So now you've got two tools in your tool belt to help you determine where these maxes and mins are. First derivative test and second derivative test. So this last example here introduces us to this new term, the point of inflection. And a point of inflection corresponds to the change in concavity. So it's when it switches from concave down to concave up, or vice versa. Those happen when the second derivative is equal to 0. So here's our statement that we want to make sure we look at and pay attention to. If the second derivative is 0 and f changes concavity, then f has a point of inflection. That means when we're doing something like one of these sign charts, we have to make sure it actually changes signs from negative to positive or positive to negative. There are some instances where that won't happen. F is considered concave down when the second derivative is negative, and concave up when the second derivative is positive, which we already talked about. So here I've got a new function, 2x to the fourth minus 4x squared plus 1. And they want us to kind of go through the entire test. So we want to find all the turning points, and we want to determine the nature of those turning points, so maxes or mins. Find where we're increasing and decreasing. Find the intervals of concave up and concave down, and then sketch a graph. So just before we get started, turning points. In order to do that, I need to do the derivative. And I'm going to set it equal to 0. And to find their nature, I can either do second derivative test or first derivative test. But since I see in part B, I want to know increasing and decreasing, again, that's first derivative. So I'm probably going to do the first derivative test here. But then in part C, concave up and concave down, I need the second derivative for that. And then we're going to sketch. So I'm going to need both. So let's start with the first derivative equal to 0 for these turning points. So my derivative here is 8x cubed minus 8x I can take an 8x out of both terms, and I'm left with x squared minus 1. So we get 8x, and then this one I can factor more, x minus 1 and x plus 1. So we get x equals 0, x equals 1, and x equals negative 1. I'm going to do my sign chart. Remember to put these in order like it's on a number line. So I'm going to do negative 1, 0, and 1. And I'm going to label my sign chart. I found these with the first derivative. All right, I'm going to start with this far left interval to the left of negative 1. I'm going to use this factored one just because it's easier to plug into. So if I pick like negative 10, this one will be negative, negative, and negative. So 3 negatives gives me a negative. Between negative 1 and 0, so I'll pick negative 0.5. That gives me a negative, times a negative, and then a negative 0.5 here would give me a positive. So 2 negatives and a positive gives me a positive. Oh my goodness, I am having trouble with this pencil. Between 0 and 1, positive 0.5. So I get a positive, a negative, and a positive. That gives me a negative. And then last, something on the right here, I picked 10. Positive, positive, positive gives me a positive. So because it goes from negative to positive, I know that x equals -1 is a min. And then here it switches from positive to negative. So I know that x equals 0 is a max. And then it switches from negative to positive again. So I know this one is another min. Now, part B wants to know where is f increasing and decreasing. I can use this same sign chart to help me out. So I'm going to just write my sentences here. So in part B, I'm going to say f of x is increasing. And I can look, I want to find these positive intervals. So when -1 to 0 and x is greater than 1. And we're going to say that's because f prime of x was positive. We can also state f of x is decreasing. And I'm going to look for those negative intervals up here when x was less than -1 and between 0 and 1. Because f prime of x was less than 0. Now in part C, they want to know where is my function concave up and concave down. So that's where I need to set my second derivative equal to 0 and do a sign chart. So here I've got my first derivative, so I'm going to do the derivative again. So I get 24x squared minus 8. And you can just solve this, so add 8 and divide by 24. So we get x squared equals 1/3. And so when we do this, we get x equals plus or minus the square root of 1/3. And I'm going to just leave it like that. So I have two answers, negative square root of 1/3 and positive square root of 1/3. And we got those from the second derivative. So if I plug one in on the left-hand interval, let's say -10 again. If I plug in -10, I'm going to get a very positive number. If I pick a number in between, I choose 0. If I plug in 0, I get a negative. And then if I plug in a number over here, I pick +10, we get a positive number. So now we can write our statements, and we can say f of x is concave up when x is less than negative square root of 1/3 and x is greater than positive square root of 1/3 because f double prime of x was positive. And then we write the same sentence, f of x is concave down between these values because f double prime of x was negative. Oops, sorry guys. And so the last thing we need to do here is sketch the graph, including any maxes, mins, or points of inflection. So here are my points of inflection, and here are all of my maxes and mins. We're just going to do a sketch. I'm going to erase this so I've got some room. I'm going to do my sketch right up here. So this doesn't have to be a huge graph. I can see my maxes and mins all happen between -1 and 1. So I'm just going to go -2 to 2 on my graph. I don't really have a Y scale written in here. And so I'm going to just kind of pick willy-nilly. Right now I don't know any details about where ordered pairs are, and I don't have to. It just told me to sketch. I'm just going to put some of these important pieces in here. I can see that there's a maximum at x equals 0, so I'm going to put it way up here. I'm just going to put a little loop, like a max up there. I can see I have a min at 1. I'm going to actually put it here. And at -1, I also have a min, and I'm going to put that one down here. I'm just picking spots, guys. You can put them wherever you want to. Just make sure if it's a min, it's below the maxes. And then here, I can see that my function is increasing between -1 and 0. So from here to here, it has to go up. And when x is bigger than 1, it has to go up. And I know my function is decreasing to the left of -1 and between 0 and 1. So far, so good. The only thing now that I need to check is that at -√1/3 and positive square root of 1/3, which is in here, does it switch from concave up to concave down? So I can see this one to the left of square root of 1/3, it should be concave up. Does it look like I have a smiley face up to about this point? And I can see, and I'm going to just kind of, at some point in here, it's really undiscernible with the eye, but in this area somewhere, it switches. So now it's went from being a happy function to being a sad function. So yes, that would be at negative square root of 1/3. Now at positive root 1/3, same thing happens. It switches from being concave down back to concave up. And so yes, somewhere in there it did switch. So that's how we're going to sketch some of those graphs.